Greetings, my name is Jean-Michel Pierre-Louis, and this presentation will be on confinement, confining materials and their effects on the strength and ductility of concrete members. Confinement can be described as the restriction of the expansion of axially loaded concrete by lateral stresses. Confinement can take the form of active confinement or passive confinement. Active confinement involves the external application of lateral stresses on the concrete to increase its strength and ductility. However, active confinement is not often encountered in the field and in practice. Passive confinement, which will be the focus of this presentation, results from the expansion of concrete due to axial stresses against a confining material like steel. Passive confinement will only be effective when the Poisson's ratio of the concrete is higher than that of the steel. And it is common practice in the field in the form of stirrups, circular, rectangular ties, and concrete-filled steel tubes. Lastly, passive confinement may or may not be continuous along the length of the member. Discontinuous confinement refers to confinement that is not provided along the whole length of the member. And this includes stirrups, circular, square, and rectangular ties or hoops. Studies have shown, it has been found that circular ties are more efficient at confining concrete due to the tendency of rectangular hoops to deflect away from corners. However, the performance of rectangular ties can be improved by the use of cross ties, as can be seen on the slide. Continuous confinement, which will also be the focus of this presentation, refers to confinement that is continuous along the whole length of concrete members. And continuous confinement is more effective at confining concrete than discontinuous methods such as the use of ties or spirals. It involves the confinement of the concrete by use of steel tubes, fiber-reinforced polymer jackets or wraps, carbon fiber-reinforced polymer jackets or wraps, and steel-reinforced grout and or other confining materials. Concrete-filled steel tubes are very effective at confining concrete, and concrete-filled steel tube columns are very often encountered in the field due to their high performance. The capacity and the ductility of concrete-filled steel tube columns or CFT columns can be significantly affected by their cross-section and overall geometry. And it has been found that circular steel tube CFT columns are more efficient at confining concrete due to the tendency of rectangular tubes to resist pressure by plate bending. Also, circular sections are generally more ductile and tend to buckle at higher ductility values than square or rectangular sections. Circular sections also tend to exhibit strain hardening behavior. And CFT members with large slenderness ratios have a tendency to fail by the outward buckling of the steel. On the slide is the plot of the axial compression ratio versus the axial compression versus the actual deformation ratio from a study of circular, square, and rectangular CFT specimens. And it can be seen on the plot that the circular specimens were much more ductile, had a greater capacity, and buckled at a much higher ductility or strain. Studies have shown that the effectiveness of CFT columns depends on the loading condition. And it has been shown that the greatest confinement occurs when the concrete itself is loaded and the steel tube is used only as a circumferential restraint. The continuous confinement provided by circular tubes can significantly increase the overall capacity of CFT columns. Circular CFT columns can also be very economical because concrete is relatively inexpensive and the greater portion of the load is carried by the concrete. The performance of circular CFT columns can be furthermore increased by the added confinement from the use of glass fiber reinforced polymer jackets or wraps. Studies have shown that the added confinement from the fiber reinforced polymer jacket or wrap will increase the confined concrete strength of the circular CFTs, will increase the confining pressure on the concrete, will increase also the ductility, capacity, and the overall performance of circular CFTs. It has also been shown that the use of fiber reinforced wrap or jacket can significantly delay and even completely suppress local buckling of circular CFTs. Lastly, it has been shown that fiber reinforced polymer wrap CFTs, circular CFTs, tend to fail by the explosive rupture of the glass FRP jacket. On this slide is a plot of the axial load versus axial shortening for circular CFT test specimens of the same diameter and steel tube thicknesses and different FRP thicknesses. And it can be seen from the plot where the number after the letter 0 is the amount of FRP layer. It can be seen that the higher the thickness of the FRP layer, the higher the ductility and the capacity of the member. The performance of concrete columns with regular transverse stirrup reinforcement can also be improved by the use of carbon fiber reinforced polymer wraps or jackets. It has been found that carbon fiber reinforced polymer jackets were more effective than transverse stirrup reinforcement for overall strength increase. And it has also been found that the use of carbon fiber reinforced polymer jackets could increase the capacity and performance of members with transverse reinforcement. They will also increase the confined concrete strength. It has also been found that the failure mode of such members was by the breaking of the carbon fiber reinforced polymer jacket. On this slide is a table showing the results of the study on the performance of CFRP confined concrete specimens with both transverse and longitudinal reinforcement. The first number next to the specimen number gives the amount of CFRP, a layer, the thickness of the CFRP layer. And it can be seen from the table that increasing the thickness of the CFRP layer leads to an increase in confined concrete strength. Steel reinforced grout is another promising confining material that has been found to increase the strength and ultimate strain of confined specimen. And studies have shown that the greater strength and ductility improvements from SRG confinement were obtained from small circular and rectangular columns confined with only 2 layers of low density fiber sheets. We can conclude that glass fiber reinforced polymer confined circular concrete filled tubes seem to offer the most effective concrete confinement. And we can also conclude that circular CFTs are a great structural and architectural solution because of both their performance and the fact that that circular members are aesthetically pleasing. Lastly, the effect of concrete confinement on the performance of concrete columns should be further investigated so that the benefits of confinement can better be understood. Thank you very much for watching.